In this week, we are going to discuss the model on functions of several random variables. In the last model, we discussed more than one random variable together that form a random vector, and we discussed the joint distribution of n-dimensional random variables. Now, in this model, we are going to discuss functions of random variables. In this topic, we are going to discuss three aspects. One is the distributions of functions of several random variables. Then the second lecture we are going to discuss order statistics. This is also one special type of functions of several random variables. Third, we are going to discuss conditional distribution. The way we discussed conditional probability of an event, we are going to discuss conditional distributions when we discuss several random variables. And followed, we are going to discuss random sum. So, these are all the three topics which we are going to cover it in this model in functions of several random variables. The first lecture is on distributions of functions of several random variables. In any random experiment, we create n random variables, but later when you start solving the problem, so we may feel we need some more random variables which is other than what we have started in the beginning. We can always create a new random variable from the scratch by the definition of random variable, then we can get the n-dimensional random variable. But it is easy to create a new set of random variable with the help of the earlier set of random variable which we have already created. That means we can create some sort of a composite function of random variables such a way that we will land up the new set of random variables. In that case, our interest is to find out what is the distribution of the new set of random variables. When we know the distribution of the earlier set of random variables, that means through the distribution of the earlier set of random variables, we are going to find the distribution of a new set of random variables. When I use the word earlier set of random variables and the new set of random variable, I am using the notation called the earlier set of random variable is x1, x2, xn. That means each one is a random variable. We have n random variables together jointly. Therefore, this is a n-dimensional random variable. The new set of random variable, I say y1, y2, y suffix k. That means the new set of random variable need not be the same size of the earlier set of random variable. So, we know the distribution of this random variable, that is known. We are going to find out what is the distribution of y1, y2, yk when we know the distribution of x1, x2, xn. For that, what we are going to do, we are going to create the relation of yi's in terms of xi's. That means yi you can think of it's a composite function with n random variables. Similarly, you can think of y2 as another random variable which is a function of the x1, x2, xn random variable. Like that we have k random variables. That means we obviously xi's are the random variable, yi's I is equal to 1 to k are going to be random variable provided the function gi's has to be Borel measurable function. So, we make the assumption gi's where I is equal to 1 to k are Borel measurable functions. The same thing what we have done it in the one dimensional random variable. When x is a random variable, g is a Borel measurable function, then y is equal to g of x, that is also going to be a random variable. The same concept we are using for the several random variables. Therefore, when xi's are known with the distribution and gi's are Borel measurable functions, then yi's are going to be the random variables. Therefore, y1, y2, yk is the k dimensional random variables. The question is how to find the distribution of yi's. That I am going to give it as the result. Suppose xi is x1, x2, xn are discrete type random variables and the joint probability mass function is known. I am discussing the concept of distributions of several random variable for discrete type random variable first, then later I am going to discuss for the continuous type random variable. Since we know the joint probability mass function of xi's, you can directly write down the probability mass function of y1, y2 and yk's jointly, that is same as probability of, you can replace y1 by g1 as a function of x1, xn, that takes a value small y1, y2 takes a value small y2, that means g2 x1, x2, xn, that takes a value y2 and so on. And for the gk of x1, x2 and so on xn, that takes a value yk, that is same as all the summation of the probability of x1 takes a value small x1, x2 takes a value small x2 and so on, xn takes a value small xn, such that all the xi's x1, x2, xn belonging to Rn. Not only that, g1 of x1, x2, xn, that is same as y1. Similarly, g2 of x1, x2, xn, that is same as y2 and so on. gk of x1, x2, xn, that is same as yk. If you make a summation over these conditions, that means all the xi is belonging to Rn, and g1 of x1, x2, xn, that is same as y1, g2 of x1, x2, xn, that is same as y2, like that gk of x1, x2, xn, that is same as yk. Finding out the joint probability of x1 takes a value small x1, x2 takes a value small x2, and so on, xn takes a value xn. That is going to be the probability of the random variable y1 takes a value small y1. Similarly, the random variable y2 takes a value small y2, and so on. The random variable yk takes a value yk. So this is a probability mass function for k dimensional random variable. So this is the joint probability mass function of k dimensional random variables y1, y2, so on, yk. So this is the way one can find the distribution of functions of several random variable when the random variables are of the discrete type and g's are Borel measurable functions, so that y is also going to be a discrete type random variable. One can get the joint distribution in this way. Let us go for one simple example how it works. The example 1. Let x1 comma x2 be a two-dimensional discrete type random variables with joint probability mass function, which is given by x1, x2. The possible values of x1 is -1, 0 and 1, and the possible values of x2, that is 0 and 1. The joint probability mass values for possible values of x1 and x2, this is 1 by 7, and this is also 1 by 7, and this is 2 by 7, and this is 1 by 7, 1 by 7, and again 1 by 7. If you sum all the values, it is going to be 1, 2, 3, 4, 5, 5 plus 2, 7, summation is 1, and if you make a row sum and a column sum, you will get the marginal distribution of x1 and x2. Now we are going to define the new random variables, that is y1 as a g1 of x1 comma x2, that is x1 plus x2, that is y1. We are defining a second random variable as a g2 of x1 comma x2, that is a product of x1 x2. x1 x2 are of the discrete type random variable, and y1 is x1 plus x2, y2 is equal to x1 into x2. Therefore, you will get y1 and y2 are discrete type random variables. Now our interest is to find out the joint probability mass function of y1 comma y2. Since it is a discrete type, you can make a table. So y1, y2. Since x1 takes a value -1, 0, 1, x2 takes a value 0 and 1, y1 takes a value -1, 0, 1 and 2. So -1, 0, 1 and 2. Similarly, one can find the possible values of y2, that is -1, 0 and 1. Now you can start filling up. Suppose y1 takes a value minus 1, y2 takes a value minus 1. What are all the possibilities in the x1, x2, so that the y1 is going to be minus 1, y2 is going to be minus 1. There is no way you will get this possibility. Therefore, the probability of empty set is 0. Whereas when y1 is minus 1, y2 is equal to 0, that is possible with the probability 1 by 7. Similarly, y1 is minus 1, y2 is plus 1, that is not possible, therefore the probability is 0. Similarly, you can fill up other elements. 1 by 7, this is 2 by 7, you can verify. 0, this is 0, 2 by 7, again there is no possibility, therefore the probability is 0, there is no possibility, this is 1 by 7. Again you can cross check whether this is going to be, the whole summation is a double summation over y1, y2 has to be 1. 1 by 7, 1 by 7, 2 by 7, 2 by 7, 1 by 7, therefore the addition is 1. Here also you can find the marginal distribution of y1 and y2 from the joint distribution. So, since this is the discrete type with the 2-dimensional random variable, and again we make a y1, y2 as a 2-dimensional random variable, we are getting the joint probability mass function of y1, y2. Suppose if it is a n-dimensional and y's are k-dimensional, still you can able to find as long as k is less than or equal to n. As long as k is less than or equal to n, you can get the joint probability mass function. So, that can be written in the previous slide. K has to be less than or equal to n. You can get the joint probability mass function of yi's, where I is running from 1 to k. This is a very easiest example. Now we will go for the little different example. Example 2. Let x be a random variable which is binomial distributed with the parameters n comma p. And another random variable y that is also binomial distributed with the parameter n comma p, same p. And I make the assume that the random variable x and y are independent. I assume that x and y are independent random variables. The question is, find the distribution of x plus y. Find the distribution of x plus y. It is easy to do because x is a discrete type random variable, y is a discrete type random variable, and we have not supplied the joint probability mass function of x and y, whereas we made the assumption both are independent random variable. So, you can use the independent concept. If two random variables are independent, then the joint probability mass function is same as product of probability mass functions of x and y. So, you can use that concept. Therefore, I can directly compute the distribution of x plus y. I will take z as x plus y. Since x is a binomial distribution, the possible values are 0, 1, 2 and n, and y is also binomial with the possible values are 0, 1, 2 and so on till n. Therefore, the possible values of z is going to be 0, 1 and so on till 2n. So, one can find the probability mass function of the random variable z for z takes a value 0, 1, 2 and so on till 2n. So, this is a probability mass function which we are going to find, which is going to be a positive, and all other points it is going to be 0. So, we will be worried about when z takes a value 0, 1, 2 and so on till 2n. So, this is same as I can replace z by x plus y takes a value small z. That is same as if I introduce a one dummy index I, that is a probability of x takes a value I and y takes a value z minus I, and all possible values of I can get the probability of x plus y is equal to z. I am just replacing probability of x plus y is equal to z, that is same as for all possible values of I with the summation, the joint probability of x takes a value I, y takes a value z minus I, that is going to be same as the probability of x plus y is equal to z. I am not going to write what are all the possible values of I very clearly, because for some I the y may not be within the range of 0 to n, or x cannot be in the range of 0 to n. Therefore, whenever the x takes a values 0 to n as well as y takes a values 0 to n, then only you will have some sort of joint probability mass function. Otherwise, those probabilities are going to be 0. Therefore, I am not going to write what is the possible values of I. I leave it as it is. Now, I am going to use the independent concept. That means the probability of x takes a value I and y takes a value z minus I, that is same as, since these two random variables are independent, I can make it a probability of x takes a value I multiplied by probability of y takes a value z minus I. That is what I made the assumption these two random variables are independent, otherwise I cannot proceed further. So, either to solve this problem I should have given both the random variables joint probability mass function for x comma y, or I would have made the assumption x and y are independent, then only I can able to find the distribution of x plus y. So, this is same as summation over I, probability of x takes a value I, probability of y takes a value z minus I. Now, you can use a binomial distribution probability mass function for x as well as y. That is what we have not discussed many problems in the earlier modules when we started discussing the standard distributions, because in the whole course we will be using those distribution again and again. So, now those who remember probability mass function of binomial distribution, you can directly write that is NCI p power I 1 minus p power n minus I. This is a probability mass function for a binomial distribution with the parameters n comma p. Similarly, you can write a probability mass function of y, that is a NC z minus I p power z minus I 1 minus p power n minus z minus I. You can go for simplification. This is p power I, this is p power z minus I. You can take the p power z outside. Similarly, n minus z plus I, and this is 1 minus p power n minus I. So, you can do some simplification, and after simplification you can get the result, that is 2n z p power z 1 minus p power n minus z. Yeah, sorry, it is 2n minus z. The way I said p power I, p power z minus I, that is killed, you will get p power z. Similarly, 1 minus p power n minus z minus I, if you simplify, you will get 1 minus p power 2n minus z. The only thing is the summation over I, nci with the multiplication ncz minus I, that is same as 2ncz. That is the result which we are using, summation of nci multiplied with the ncz minus I, that is same as 2ncz. So, this is a probability mass function of the random variable z, and the possible values of z is 0, 1, 2 and so on till 2n. By seeing the probability mass function which is greater than 0 in this value, 0 otherwise, you can conclude the random variable z, which is also binomial distributed with the parameters. You have to map the probability mass function of this with the probability mass function of binomial distribution. Then you will conclude that is parameter is 2n comma p. So, this is a use of named or standard or common distribution. You don't know the distribution of z, you are finding the distribution of z. After you get the probability mass function, this is same as a probability mass function of a binomial distribution. Therefore, we conclude z is also binomial distributed with the parameters 2n comma p. Now, one can discuss some what if scenario. Suppose x takes the binomial distribution with the parameter n comma p, whereas y takes a binomial distribution with some other parameter instead of n. Suppose you treat some other positive integer m, but the next parameter is same p. Let me write. Suppose x is binomial distribution with n comma p and y is binomial distribution with some other parameter m comma p, and again I am making the assumption both the random variables are independent. Then also you will get a binomial distribution with the parameters n plus m comma p. That means if you have a two independent binomial distribution with a different n and m, whereas the probability of success in each Bernoulli trial p is same for both the random variables, then the sum is also going to be a binomial distribution with the parameters sum of those first parameter comma the second parameter is p. That means this can be extended for any n random variables. Suppose each random variable is binomial distributed with some number, some positive integer with p, and all are going to be a different number for first parameter, then the sum is going to be again binomial distribution with the sum of first parameters with second parameter is p. So, this can be generalized into any n mutually independent random variables. Since we have two random variable, we are using the word independent random variable. Once you have more than two random variables, for any n mutually independent random variables, each one is binomial distributed with the same probability of success p with the different parameters in the first one, then the sum is also going to be binomial distribution.